So, welcome back. So, in previous lecture we discussed about the forecasting and prediction of earthquake, and there were few successes which were been achieved in prediction or forecasting the earthquake. One was the 1975 Haichen earthquake of China, and there was another one from Himalayas. So, today we will discuss about this and we will move further in this lecture. So, as we discussed in the previous one, that there is a quiescence of the large magnitude earthquake greater than or equal to 7.5 between the period from 1953 to 2001. So, an early case for recurrence interval. The other studies which were been taken up in the areas like the affected area by Shillong earthquake, which was in 1897 with magnitude 8.7. The group from National Geophysical Research Institute NGRI, Dr. Sukija and his team have reported the result of paleoliquefaction. So, these are the secondary effects which will always get preserved in the sediments, and this is because this is related to strong ground shaking. So, they found the evidence and the periodicity of the large prehistoric earthquake in this region, and based on the radiocarbon ages of collected the charcoals collected from different units which were been deformed due to the liquefaction process. What they suggested was that the recurrence interval in this region is almost like 400 to 600 years. So, this study was been done in the area of northeast India in Himalayan region. A moderate magnitude earthquake forecast was been done, and this was been 1988. This was been done in 1988. So, the global effort towards establishing the precursory pattern that precede major and great earthquakes. So, this is what was been taken into consideration for the Haichen earthquake also, that the precursory events were been considered for predicting the preceding major events. So, a swarm or the quiescence preceding major earthquake also is an indicative of that. So, either there is number of earthquakes, a large number of earthquakes have started occurring in a particular region, or there is a quiescence, there is no earthquake which has been recorded since last 100 years or 50 years or so. Those areas are the areas which will be hosting the large magnitude earthquake. So, considering this, either it is a swarm or the period of quiescence, and taking into consideration the process of precursory events, similar exercise was carried out by Gupta and Singh in 1986 and 1989 in the vicinity of Indo-Burma border. Now, based on this, August 1988 earthquake was been predicted. Okay. So, this is the northeast portion of India, where the previous record, it suggested that there was an earthquake in 1897, and then another one was here in 1950, and few more which are been listed here 1947, 1905, 1931 and all that. So, in this region this was been predicted, the earthquake was been predicted. So, Gupta and Singh in 1986 discovered one such region shown in the image. This is one side, and predicted an earthquake that may occur at any time from then onwards. Okay. So, they suggested that during their studies and carried out in 1986. So, after this any time there will be an earthquake in this region. What they also suggested that this was definitely based on the precursory events. So, they emphasized that this event that should the predicted earthquake does not occur till the end of 1990, okay, then this forecast could be considered as a false alarm. Okay. So, this uncertainty always remains with the observations or with the studies which are, or the investigation which are carried out considering the precursory events. Okay. But at least if there is the forecast based on such studies will alert the people in the local area or the respective areas where such predictions are been done, and precautionary measures can be taken up well in advance. Okay. If it is false alarm, it is well and good, but if it occurs, then we are towards the safer side. So, however, it turned out a true alarm, okay, and there was an earthquake which occurred when on the forecast was this one and the occurrence is over here. So, what they suggested that this will be the region where the earthquake will occur, and the magnitude will be around 8 plus minus 5, okay, 0.5. So, but the earthquake occurred in this area as compared to what was then given the region here, which was very much within the predicted area. Okay. If you can see this one here, it lies very much close to this one. Okay. So, it occurred within that, and the depth also was been predicted that the depth will be around 100 kilometers from the surface, and the depth was 90 kilometers, which was, and time which was been given was between like from 1986 and December 1986, okay. And the earthquake occurred in 1988 on August 6th. So, this was again another successful achievement which was been done based on the precursory events. Now, earthquake focus and hypocenter. So, wherever there is a maximum amount of energy is been released at a particular point, that is termed as your focus on the fault plane, and the exactly the location on the surface has been termed as epicenter, and the displacement which has been observed on the surface, if there is a displacement coming right up to the surface, then the deformed surface has been that manifestation of the deformation has been termed as fault scarp, and the line here along which the movement has taken place is the fault line. So, this will be the fault plane, this will be your fault line, and the displaced surface is your fault scarp. So, the energy where it has been released, the stored energy at depth is termed as focus, and the point exactly on the surface above that is your epicenter. So, for us everything is all these points are important, but to know that at what depth the earthquake will take place, what is the epicenter, the fault line, and whether we see the signatures which are preserved in the landforms on the surface, that is your fault scarps and all that. Now, depth one can easily pick up, because this also helps in understanding that what is the pattern of faulting, okay, because whether the fault is dipping in this direction or the fault is dipping in this direction, this one can pick up based on and what is the depth. So, simple exercise can is been done considering the distribution of earthquakes. Now, this is the case where 2001 Bhuj earthquake occurred, and these are all aftershocks. So, aftershocks have been distributed in the area which got ruptured, that is subsurface. Okay. So, what you see is this is of course is the plan view. you see the distribution along the latitude longitudes, and these are the location of those epicenter, and these are all pitch and ball diagram, which also indicate and which type of movement has been observed along this one. Either the block has moved up, or either it has laterally moved, or it has moved down. Okay. So, the location of earthquake has been done, as I have briefly discussed, that the instrument which has been used to record has been termed as seismograph, and the recorded graph which we get is been termed as seismogram, and this is mainly where the arrival time of the difference between the arrival time, that is an S and between the S and P wave, or you take between the Love and Rayleigh wave, they take the difference has been taken into consideration along with the amplitude to locate the epicenter. So, this is another diagram along with that, which shows that not only the location of the epicenter is important, but for the civil engineers and as well as the seismologists, they will be interested in knowing that what is the amount of horizontal movement and what is the amount of vertical movement which has been taken. So, this it shows that there is the horizontal movement and what will be the vertical movement. Okay. So, this basically records the ground shaking. So, although many seismograph stations now records earthquake wave digitally, a recorded drum seismograph like this one is specially used for visualizing the nature of earthquake waves, that is mainly their amplitude, wavelength, and the frequency of the vibrations. So, different seismographs are used to measure, for example, which has been shown in B, horizontal version and the vertical motion. So, the vertical as well as horizontal motion is also important, because that will help us in understanding that if a particular earthquake has been triggered in any given region, then what will be the effect to the site of interest where we want to go for seismic hazard assessment. So, basically if you are having the seismograms, okay, so the difference between the arrival of P wave and S wave has been taken into consideration, and that helps in, and along with that the amplitude has been taken into consideration. So, the example which has been given here, where it shows that you have considered the amplitude of the arrival of the different seismic wave, but mostly it has been taken as an S wave arrival, because this will result into the major deformation. The P wave is mostly the compressional, but this one is the shear waves, that is an S wave, and the difference between the arrival. So, this will be arriving first and this will be later, and the difference has been taken here, and this is a log scale which helps in locating that or identifying the magnitude of the earthquake. So, you have the amplitude here, you have the time difference, and connecting these 2 points will give you in the chart will give you the magnitude and what was the magnitude of that particular earthquake. So, the Richter scale, if you take because the amplitude will play an important role, what we are seeing here, the difference between the magnitude 5 and 6 is very, very large. Okay. And that what has been we all know that the magnitude, if we have between 5 and 6, then the energy which has been going to be released will be almost like a factor of 30. So, here we have the magnitude 6 amplitude, which you see here is quite comparatively larger as compared to what you have the magnitude 5. So, it says an earthquake of magnitude 6 registers with 10 times the amplitude as an earthquake of magnitude 5 from the same location. Okay. and this is just the differences one on the Richter scale. Now, if you have because the important part will be to locate the earthquake, that is an epicenter on the surface. So, at least you need 3 stations, 3 seismograph that will help you in locating the earthquake. So, if you these are standard diagram, the curves which are available, which helps in locating the earthquake. So, you have the if at least you have the arrival time difference between the arrival times of P and S wave at 3 different locations, you can calculate the distance, and that distance is your what we call the radius. You can plot it based on that, okay, and that the intersection of these 3 points will, or 3 circles, will give you the epicenter. So, locating earthquakes, basically you have like 3 locations which are been given here. So, you have one station which is sitting in SOCO, then TEIG and SSPA. So, these are the 3 stations which were used to locate the epicenter of one particular earthquake here. So, what it shows on this curve here, or this graph, that you are having the distance here, and this is your the time difference. Okay. So, you have the first P wave which is arriving here was at 1.5 minutes, okay, and the distance which was been calculated between the differences is here is 1.5 minutes, which is equal to 900 kilometers, and the this has increased the time because from the epicenter the wave have traveled. So, the time interval has increased. So, this is around 3 minutes 1800 kilometers, and further if you go away, that is your SSPA, this one is SSPA, the time interval is almost like 5 minutes, okay, and that has given the larger distance from the epicenter. So, as you move away from the epicenter, so suppose the earthquake has been triggered here. So, the arrival time at this station will be comparatively less, here will be a little more, and this will be the largest one. So, that is what one can observe based on the arrival time difference. Okay. So, the difference in the arrival time between the P and S wave reveals the distance from a particular seismogram and to an earthquake, that is the distance from here to this one here. So, this plot shows the record from seismographs at different locations or different distances from a single earthquake. For typical crustal, because the time interval is almost remains in that, because the first arrival and the arrival of P wave and S wave depends on because of the nature of the P and S wave traveling through the different medium, and in crust mostly what we see is the travel the velocity remains around 6 km per second for the P wave and around 3.5 kilometers for the S wave. Thus, the distance for the recording station to the earthquake focus is given by, so this is an equation which has been given, which can help you in calculating the because you need the time and you need you know the velocity which has been given here. So, based on that, this is the Ts is the travel time for the that is the arrival time of your S wave, and this is P wave, and then you can use the values putting in this equation and identify the distance. Okay. So, the Tp and Ts are the arrival time of P and S wave respectively. This distance defines a circle centered on the location of the station upon which the earthquake focus must lie. Okay. Now, in some places or some stations will not allow you exactly to have an intersection here. So, the in between area has been taken initially as an epicenter, and then with the data coming from more stations, because not all regions will have at minimum 3 stations, they might be having more stations. So, if more data comes in, then you can refine the location of the epicenter. So, this is the similar example which talks about the different seismographic stations reveals the location of earthquake epicenter. So, seismic waves from an earthquake moves out concentrically from the focus and arrives at distant seismographic stations at different time. Okay. So, as we were talking about that if you are having the differently located seismograph, then you will have that they will arrive at different time. Then the second one, it tells us that the graph of the time interval. So, you are having the time interval here which has been given here, and then you have the distance which has been highlighted here. The previous diagram was also more or less similar. Okay. So, what we see as the travel time versus distance is called the travel time curve. So, we have the travel time curves available because the P wave travel almost twice as fast as the S wave. So, this will arrive first and this will arrive later, because the velocity is around 6 and this is almost around 3.5 or so. The interval between their travel time curves increases with distance. Okay. So, that what was been explained in the previous slide also, that in the arrival time here will be less because they are close to the epicenter, but the difference between the arrival time increases as you move away from the epicenter. So, by matching the observed interval to the spacing of the curves, a geologist or the seismologist can determine the distance from station to epicenter. An 8-minute interval occurs at about 5,600 kilometers from the epicenter, which has been shown here. Okay. So, if you have 3 minimum points, then one can easily locate the earthquake epicenter. Now, since we have very fast computing facilities and algorithms which are available with us, so this seismographic stations can very quickly calculate and tells us that where exactly the epicenter is located. So, in no time, maybe in few minutes or maybe in less than a minute, you will get the location of the epicenter. Along with that, there is another exercise which has been done, is your identifying the different type of faults or the slip which has occurred, and this has been done considering the arrival of the first motion, that is the arrival of the first wave. Now, not all the stations will have the similar arrival, that is what you are having here positive wave, but here first motion is your negative and so on. Okay. Now, this will indicate that what is the pattern of movement which has occurred in that particular region. So, what it shows is here you are having the fault line, okay, and at least you have the 4 stations, for example, which are located here, and based on this you will be able to pick up and identify that what type of movement has occurred along this one. So, this fault geologically we understand that this is a right lateral fault, and what we see based on the or observe considering the arrival of the seismic waves. So, 4 seismic stations are put with respect to the fault line here, and during an earthquake the first arrival wave, this what is shown is the positive one, and this one is also positive one on this side. So, this shows push away from epicenter. Okay. So, this has been pushed away, this area has been pushed away from the epicenter if the epicenter is here, for example, and and this also push away from the epicenter, whereas this one is a negative. So, this pulls towards the epicenter. Okay. So, you have the pulling towards one another, and these two blocks are pushing away from one another. Okay. So, the first motion of the P wave arrives at the seismographic stations is used to determine the orientation of the fault plane and the direction of slip. The case shown here is for the rupture of right lateral strike slip. So, you are having a right lateral strike slip. Note that the alternative pattern of pushes and pulls would remain the same. Okay. So, this remains the same if the plane perpendicular to the rupture with left lateral displacement has been taken into consideration. Okay. So, seismologists can usually choose between the two possibilities using regional information such as field mapping of the fault trace. So, what we are trying to tell here, this one or you consider this one here, then the motion remains the same here because what has been recorded, but based on along with the seismological information, the field information is extremely important. Now, this type of exercise helps us in identifying the fault types. Okay. That is what we call the either it is reverse fault, normal fault, and the diagrams which we get is been termed as pitch ball diagram. Okay. So, we have in case of the normal faulting, you will find which has been shown that you have the one block is moving away. So, there is an extension here, and this shows the compression here. This is in the case of the reverse fault, whereas this in this case you have compression here, you have the extension along this one. Okay. So, I will stop here and we will continue in the next lecture. Thank you so much.